So that's the formula for, this C is not charge, this C is capacitance. This one is capacitance. And so you have this constant because it's a vacuum. This will change if you have a dielectric, as Kenta said. Your constant will change. We just call it something else, or we put a K in front of it. This is the important part. So what happens if I increase the area? Good. Eric, increase capacitance. And if I increase capacitance, what can I do?
Store more charge.
Yes, I can store more charge. If I decrease the distance between the plates, what happens? Capacitance up, and I can store more charge. So directly proportional to area, inversely proportional to the distance between the plates. Is that going?
Yeah.
Thank you. What else? Yeah. Okay. So. You also have K.
That's key. That's key.
The dielectric constant. And that's the coating that we put on there, the little stuff in between the plates. And then we say K times the permittivity of free space just becomes somewhat confusingly. Is that an epsilon?
Yeah.
Is it like a little epsilon?
Yeah. This formula is not on the book.
This one's not?
Yeah.
Oh, that's interesting. And so if the capacitor has a dielectric, they don't all, but most of them do. Then C is equal to just epsilon A over D. It's a small difference, but it's kind of a big one because this varies with the type of dielectric, whereas if it doesn't have a dielectric, it's just epsilon naught. Okay, so let's talk a little bit about the energy that we store in a capacitor. Let's just have a quick little thing with units. What electrical unit has energy in it? So joules. What unit has a joule in it? Voltage. Thank you. Thank you. So a volt is what?
Energy per charge.
Very good. So 1 joule per coulomb. Yes? So if you have a circuit with 1 volt pushing on your capacitor, the number of coulombs of charge in the capacitor would give you the number of joules stored. Does that make sense? Okay. The trouble is that when you're charging the capacitor, the push is not constant. So let's do like time and charge. If a capacitor is charging up, maybe I won't do time. Let's do voltage. when you start, let's say you have your circuit with your plates and everything, and you have your 1.5 volt battery, and you open it. There's 1.5 volts pushing on those plates, right? When it stops, you have kind of zero force then. Does that make sense? Like, it's not gonna be, it's like stretching a spring. When you start stretching the spring, it's really easy. It's actually nothing, right? And then when you stretch it just a little bit, it's a little bit of force. And then you stretch it all the way out and you get to the end and you get to that full spring force, right? It's the same with the capacitor. When you start pushing it, it doesn't really take any force at all. And then when the capacitor starts to get full, it takes more and more force to squish that last bit of charge in there. Does that make sense? Okay. So the average energy charged, the average energy stored is half QV. So the potential energy is 1/2 times the charge times the voltage. So this is a joule per coulomb and this is a coulomb, so you end up with joules, right? But it's half because it's not it doesn't just happen. You have to fill it up at some rate, right? Okay, and so Q, we know, is what? What's the formula for Q? CV, right? So let's put that in there. So we have half CV times V, which is going to be 1/2 CV squared. And of course, you could also say this is 1/2 Q squared over C. I believe. And then if you say, okay, we said that our let's do this this way. Do you guys know this? Do you know how voltage varies with energy between two plates? Okay. Voltage across two plates is the energy times the distance between the plates. It's actually back there in the middle. C, we said before, was epsilon naught, or epsilon if you have a dielectric, times A over D, right? Just take a minute, put those together and see what you come up with.
Is the voltage across the plates, or is it the voltage of the supply?
Yes.
Oh.
Should be the same. When it's charged, it'll be
Okay.
the same.
Wait, is it not epsilon naught?
Yeah, let's put the naught in so we're clear. it's gonna have to be squared, and then you're gonna have A D. And this is all potential energy stored. So if you know your epsilon of your dielectric, you can have your field, and then you have area times distance. Did I say this E was energy? This is not energy. Let me be clear.
What?
This E is not energy. This is electric field. I think I said energy before.
Yes.
That's wrong. This is not energy. This is energy. Like we're all solving this all for energy. But this is for electric field. This is why you sleep before your IB exam. So you look, you see that E, and you're like, that's electric field. But if you went to the Canadians home opener last night and enjoyed yourself, you might see that go energy. So don't do that. Yeah, this is electric field, which makes sense, right? Field is force per meter.
The D again?
Say that one more time.
The D.
The D is the distance between the plates. And then if you know the area of the plates and you know the distance between them and you multiply those two, what does that give you?
The cube, like the box.
Yeah, it's the volume of the space between the plates, right? So you can also get energy density. Yeah, bless you. So the energy density is just half epsilon naught times the electric field squared. So if you know the field, you can just multiply it by the permittivity, or you just got to square the field and multiply it by the permittivity and multiply by half, and that will give you the energy per unit volume between your plates. There is a 4 pi in that epsilon, but it's 1 over 4 pi k. But which k is it? Oh, it's
The spring constant.
I don't think it's a spring constant. Do you guys care about the constants?
I don't think, I've never seen the IB exam put that what the K equals.
The one with the k?
Yeah.
Okay, let's not worry about
The
it
one
then.
for permittivity. It's like,
Jeffrey's not here, we can do what we want.
I just think K is just a constant for dielectric.
No, to get your 8.85 times 10 to the negative 12,
Okay.
it's 1 over 4 pi k. I think it's Boltzmann's constant. It doesn't matter, you don't need to know. Okay, I'm gonna give you some
it's the Coulomb constant apparently.
Coulomb constant.
I don't know.
8.99 times 10 to the
That's
9.
just the 1.6.
Is it the 1.6?
That's Coulomb.
I'll look it up, I'll figure it out. I'm gonna give you some problems and you guys can do a little bit of practice on this, and then we're probably gonna be pretty much done after that. So Giancoli, if you go to page 524, and you can do 30 to 37, and don't do the ones that, if you look at it and you go, yeah, I know how to do that, just, you know, judge accordingly. But this is good practice for this capacitance stuff. And There's a little bit more to it, but we could probably stop there because it's gonna be too much work. How many more classes of this do we have?
Friday.
There's a little bit more for the charging up and like the charge and the discharge.
You don't need to know charge up, you don't need to know discharge.
Say that again.
You only need to numerically know discharge.
Really?
Yeah, charging up, they don't care about.
They don't care about the charging up?
Yep.
Oh, that's nice. Should I just give this to you right now then and then we'll be finished capacitors? Or are you tired? Do you need a break?
We don't have time for a break.
You don't have time for a break, okay.
We could probably stop filming that. We could stop filming.
Do you want me to do it? Should I do part 3? How long is it?
It's about 20 minutes.
Okay, this is end of part 2.